Numericals related to magnetic field produced by a wire and a circular coil. Numericals are related to magnetic field produced due to the current. Now example 1, 5 ampere current is flowing in a wire, in a long wire. Find the magnetic field produced due to this current at a distance of 10 centimeter from the wire, at a normal distance 10 centimeter from the wire. Also find the direction. Of magnetic field at point P and Q as shown in figure. This is the long wire. This point is P. Here is point Q. This one is 10 centimeter. Also 10 centimeter. Now the solution. The distance of both the points P and Q is same from the wire. It's perpendicular. Normal distance is 10 centimeter. It means the magnitude of the magnetic field on both the points P and Q will be same. Magnetic field at P and Q. At P and Q will be same in magnitude. That's B at P is equal to B at Q. That mu naught I upon 2 pi and R. Here mu naught is 4 pi into 10 raised to the power minus 7 and W of R is 10 centimeter, or you can write in SI, that will be 0.10 centimeter. Current I is 5 ampere. On putting all these values, BP is equal to BQ, that's 4 pi into 10 raised to the power minus 7 into 5 divided by 2 pi into 0.1. This pi is cancelled 2 times, means that's BP is equal to BQ, that's only 10 raised to the power minus 10 and that's 100, 10 raised to the minus 5 Tesla. Now, what is the direction of magnetic field at point B and at point P and at point Q? It is given by right hand thumb rule. This one is wire, long wire. This point is P. Draw a circle. This shows the magnetic line of force. This point is P. This point is Q. Current is flowing in upward direction. That's I. If we hold this wire in our right hand in such a way that thumb shows the direction of current, then the direction of magnetic line of force will be in this direction. Draw tangent at point P. This will be the tangent at point P. Here the tangent will be in this direction. It shows the direction of magnetic field at point P and Q. The direction of BP. The direction of BQ. It means at point P, the direction of magnetic field will be perpendicular to the plane inward. Here it is considered that the wire is placed at the paper board. Inward, it is denoted by this cross sign. It shows the magnetic field produced perpendicular to the plane inward. This way, at point Q, the direction of B magnetic field of magnetic field will be perpendicular to the plane outward. Perpendicular to the plane outward is denoted by the symbol dot this way. So the direction of magnetic field perpendicular to the plane outward. Now the second example, two plain long wires as shown in the figure are placed parallel to each other. Two long current carrying wires are placed at a distance d, that's 50 cm, distance of 50 cm as shown in the figure. Find the magnetic field at the midpoint between the wires, at the midpoint P. These are the two wires placed parallel. Here is current I1, that's 1 ampere. Here is current I2, that's 2 ampere. This distance is given by 50 centimeter. A point is here, it is 25 centimeter. This point is P. We have to find the magnetic field at this point. Now the solution. We want to find the magnetic field at point P. This is the midpoint of the wires. It means the distance of this point P from each wire will be same, that is 25 centimeter. Current through one wire is 1 ampere and through second wire is 2 ampere, but the direction is same. First of all, we will find the magnetic field due to first wire at point P. Now the magnetic field at P due to current I1, that is, suppose V1 is equal to mu naught I1 upon 2 pi and R. Mu naught is 4 pi into 10 raised to the power minus 7 into current is 1 ampere and 2 pi into distance is 0.25 meter. This one is cancelled, that's 2 only. It means V1 is 2 upon 25 into 10 raised to the power minus 5 Tesla. The direction of this one is given by right hand thumb rule. Hold the first wire in our right hand in such a way that thumb shows the direction of current, then at point P, fingers will be inward. It means magnetic field V1, the direction of magnetic field V1, that will be inward, perpendicular to the plane. It is perpendicular to the plane inward. Now the magnetic field due to the second wire, magnetic field, the current I2, let's suppose B2, that will be mu naught I2 divided by 2 pi tan same into 0.25. Here is 2 pi into 10 raised to the power minus 7 and the current is 2 ampere divided by 2 pi into 0.25. This one is cancelled 2 times. That's V2 is 4 upon 25 into 10 raised to the power minus 5 Tesla, and direction again is given by the right hand thumb rule, because this point is towards left of the second wire. So by right hand thumb rule, the magnetic field at point P V2 will be perpendicular to the plane outward. That will be, it is perpendicular to the plane outward. So the net magnetic field at point at P will be V1 plus V2, but they are in opposite direction. So V will be 2 upon 25 into 10 raised to the power minus 5 minus, or we can also write here, plus 4 upon 25 into 10 raised to the power minus 5. The direction of this one is given by it is outward, it is inward. So we can also write that V will be, it is 25, 2 upon 25 into 10 raised to the power minus 5 Tesla. That's direction of this one will be perpendicular plane outward, perpendicular to the plane. Now the example third, 10 ampere current is flowing through a wire placed in north-south direction. Direction of current is towards north. Of current is towards north. Find the magnetic field at a point at 10 centimeter above the wire. Now the solution, V is mu naught I upon 2 pi r, that's 4 pi into 10 raised to the power minus 7 into 10 upon 2 pi into 0.1. This one is cancelled 2 times, that's 2 into 10 raised to the power minus 5 Tesla towards west. Now the numericals related to coil, current carrying coil. Numericals related to current carrying coil. Example 1, 1 ampere current is flowing through a wire through a coil of 100 turns. If the radius of the coil is 1 meter, then find the magnetic field intensity at the center of the coil. Now the solution, number of turns in the coil, that's N is 100. Current through the coil, that's I is 1 ampere. The radius of the coil, R is 1 meter, and magnetic field, that's V is mu naught Ni upon 2R, that's V is mu naught means 4 pi into 10 raised to the power minus 7, N is 100, I is 1 ampere divided by 2 into 1, that's V is 2 pi into 10 raised to the power minus 5 Tesla. Example 2, find the magnetic field at the center of the coil in the following figure. Find the magnetic field at the center of the coil. Number first part, that's A, that is the coil. Current is I is 1 ampere, this one is R, this is 1 meter. Center. Now the B part is (90°). Current is 1 ampere. Now third part is I is 1 ampere, 60°. The center O. Radius in each figure, that's R is 1 meter, that is R is 1 meter. Now the solution, figure A, the semicircle, current is flowing I due to only coil. This one is R, current is flowing I is, that's 1 ampere. Number of turns will be half is 180°. 180 degree. Now the solution, number of turns, that's n will be 180 by 360, that's half. I is 1 ampere and R is 1 meter. Current I is 1 ampere and radius R is 1 meter. Magnetic field B is mu naught and I upon 2R. The value of mu naught is constant. B is 4 pi into 10 raised to the power minus 7 into N is 1 by 2 into I is 1, 2 into 1. That's B is pi into 10 raised to the power minus 7. That's 3.14 into 10 raised to the power minus 7 Tesla. Now the second part, here is this one. The angle by the circular part at the center is 90 degree. 90 degree. Current is 1 ampere. Current I is 1 ampere. And R is same because R is 1 meter. I is 1 ampere. And number of turns N is 90 by 360. That's 1 by 4. So magnetic field V will be mu naught and I upon 2R. B is mu naught means 4 pi into 10 raised to the power minus 7 into 1 by 4 into 1 divided by 2 into 1. That's B is pi by 2 into 10 raised to the power minus 7 Tesla. Now the third part, C part is given and the current I is 1 ampere. Here is the center. This is R, 1 meter. Current is flowing in this direction, 60 degree. I is 1 ampere. This point is O. Here also R is radius of coil is R is 1 meter. Current I is 1 ampere and number of turns, that's N is 60 degree divided by 360, that's 1 by 6. Because of magnetic field is given by B is given by mu naught and I upon 2R, that's B is 4 pi into 10 raised to the power minus 7 into 1 by 6 into 1 divided by 2 into 1, that's B is pi by 3 into 10 raised to the power minus 7 Tesla. Now example third, find the magnetic field at the center of the coil as shown in the figure. Find the magnetic field at the center of the coil as shown in figure. This circular coil is a long wire. Current I is 1 ampere. Center O. This one is radius R is 1 meter. Now the solution. We want to find the magnetic field at point O. It is due to the straight long wire and also due to the current in the coil. Now the magnetic field at O is due to number 1 straight wire, long straight wire, and number 2 due to circular coil. So first of all we will find number 1 magnetic field at center due to wire, straight wire. That's suppose V1 is mu naught I upon 2 pi R. I'm putting these values 4 pi into 10 raised to the power minus 7. Current is 1 ampere and 2 pi into radius is also 1 meter. That's 1 only 2 into 10 raised to the power minus 7 Tesla. The direction of this V1 is given by right hand thumb rule. If we hold this wire on our right hand in such a way that current shows the thumb shows the direction of current, then the field V1 at center will be perpendicular to the plane of the coil outward. The direction of B will be perpendicular to the plane that's outward. It is perpendicular to the plane outward. Now the magnetic field due to circular coil, that's V2. V2 is mu naught Ni upon 2R. Here N is 1. Now all of the quantities are given. So V2 will be 4 pi into 10 raised to the power minus 7 into number of turns 1 is current is 1 upon 2 into 1, that's 2 pi into 10 raised to the power minus 7, that is Tesla. Direction of this V2 is given by same right hand thumb rule. If we hold this coil in such a way, right hand in such a way that thumb shows the direction of current, then V2 will be perpendicular to the plane of the coil inward. That will be inward cross perpendicular to the plane inward. Then the net field at center V will be V1 plus V2. That's V is 1. Here is V2. Okay, that's V1 plus V2. V is upward, and that's 2 into 10 raised to minus 7. 2 into 10 raised to the power minus 7. That's inward plus 2 pi into 10 raised to the power 2 pi into 10 raised to the power minus 7 outward. Yes, inward this out. So net B will be 2 into pi minus 1 into 10 raised to the power minus 7 perpendicular to the plane of the coil inward.